Hello friends, today let's solve shortest path to get all keys. The problem is similar. We are given two-dimensional grid, but we have the dot, the at, and the smaller letters are keys, and the the lowercase letters are keys, and the capital uppercase of the letters are locks. And we start at the starting point, which is at. And one move consists of working one space in one of the four cardinal directions. We cannot work outside the grid or work into a word. So if we work over a key, we pick it up. We cannot work a lock unless we have the corresponding key. So it seems quite similar. So what algorithm have come out? First is the two-dimensional, and this is unweighted because we can go for four directions. They both have the length of 1. And we also need to find the shortest path. So it indicates that we can use a BFS algorithm, but it's different from the previous questions. Why? Because we must exit. Although in previous questions, we also need to exit. We use a weighted array in a BFS template or a typical BFS problem. But in the question, we can turn back. If we just use a 2D array named weighted to mark whether we weighted a cell or not, this doesn't work. Why? Because in that BFS template, we cannot turn back. We can only weight one place once. But is that true? We can only weight one cell once. Yes or no? And the answer is yes and no. Why? You can weight the one place once, but that only under the condition that the current keys you connect is fixed. What does that mean? You can weight this cell many times, but only when every time the keys you connect are different. Because when you weight here, you can connect it or not. When you weight here, you can only connect this A, or you already connect A and B, or you only connect B, something like that. So in each cell, we think you can have many states. Each state indicates how many keys you have connected. So in that case, we cannot use one 2D array to mark whether we weighted a cell or not. We should use a 3D array. And the third dimension indicates the current key state. That is how many keys we have connected. And you will notice that the data is quite small. We only have, at most, 6 keys. So 6 keys, how many states at most? 2 to the power 6. Why? Because for each key, we can either connect it or haven't connected. So it has 2 possibilities for each key. So that's it. Why do I mention it? Because in that case, for the third dimension of the weighted array, we can just use quite small number. Well, let's see what the algorithm goes. If we meet a sharp, we continue because we cannot walk over. If we meet a capital letter, we check whether we have the corresponding key. And it is unweighted. If it's unweighted, we set it at weight and enqueue that position. The overall algorithm is still BFS, but just minor changes. If it is a lowercase letter, if we haven't connected before, that means that cell, if we connect it, And that place we haven't visited before. We include that place and set it visited. This part is a bit complicated because we first try to connect that key and we check whether that cell has been visited. So that's the logic here. If other cases, either it's a dot or at, you cannot just write whether it's a dot because for the starting point, you can visit afterwards. So you can just use else. If it's unvisited, we set it as visited and include that place, that cell. So how to indicate whether we connect a key or not? As I mentioned before, we only have 6, at most have 6 keys, so we can use 6 bits. So that's the bit manipulation comes over the page. For example, if we only have 2 keys, how many states? For the 2, we know the keys are A, B. So for the 3 keys, we know the keys are A, B, C. So you should notice that it's sorted. I mean, they are fixed. If we have 4, you know the keys are A, B, C, D. So it's much simpler. Okay, so in that case, if we set these 2 bits both to 1, that means we connected both A and B keys. So what is the decimal number? Should be 2 to the power of 0 plus 2 to the power of 1 and equal to 3. And if we connect only the key A, we haven't connected the key B. That should be 2 to the power of 0 plus 0 is equal to 1. So for the 2 keys, at most the largest decimal number should be 2 to the power of 2 minus 1, right? It's a 3. So this is an important thing, okay? So we just translate these 3 cases into code. If we meet a capital letter, we will check corresponding bit to see whether it's 1. If it's 1, that means we connected that key. We can go over it. Otherwise, we cannot continue. I mean, we cannot walk over. So how to check it? We'll see the bit manipulation afterwards. If it's a lowercase key, we want to set the corresponding bit to 1. If unvisited, we set it visited and include that cell. So the question becomes how to check a given number, its case bit is 1 or not, and how to set its case bit to 1. Well, this is the basic bit manipulation. We want to check the given number n. If its case bit is 1, we just need to right shift n to k bits, and we this is the AND operation with 1. If it's equal to 1, that means the case bit of n is 1. How to set it? We just let 1 left shift k, and if we let 1 left shift k, that means that case bit of 1 is 1. So we set this case bit of n to 1. So this 2 operation is important. This used to check whether we already have this key. This used to connect that key. So time complexity is also simple, just m times n times 2 to the power of k. Why is m? M is the rows, n is the number of columns, k is how many keys we have. The same for the space complexity. So now let's write the code. So first, we still have 4 directions. So we just write the 4 directions. There will be 0, 1, and 0, negative 1, and 1, 0, and negative 1, 0. So here, we first get m will be grid dot length. N will be grid 0 dot length. That will be the length of this string. So this is string. It should have the parentheses. Okay. Then we need a queue. So here we will put integer array, so Q. And here you can use a linked list or array deck, up to you. Then we have to offer, in Q this at, so we need to iterate the grid I++ for int j equal to 0, j less than nj++. So we get the current char, which will be grid I char at j. We see if char equal to at, this is the starting point, we enqueue that, we offer it. So we shall put the coordinates, that will be ij. But we also need to know how much steps this moves. So at the beginning it's 0. We also need to save the key state. How many keys we have connected. So what should we put here? At the beginning it should be 0. Else, because we don't know how many keys we have, so we also need to count how many keys we have. If it's a lowercase letter, we know it's a key, so count will increment by 1. Okay? So do you know what's the keys number if we connect all the keys? For example, if the count is 2, if we connect all keys, it should be 1, 1, right? The bit all set to 1. So what's the number? The decimal number should be 2 to the power of 2 minus 1, right? It's 3. Okay, so if we connect all the keys, this key will equal to 2 to the power of count minus 1. It's the same to left shift 1 to count minus 1. It's the same. Okay. So we know this final step. Then we just do the things. If the queue is not empty, we pull something from the queue. Okay, then we get the x will be cur 0, the y will be cur 1, and the steps will be the cur 2. Also, the current key state will be the cur 3. So what's the exit condition is that if we successfully connect all keys, that means the current key equal to the keys, which are return steps. Otherwise, we just try the full directions. So full direction in directions. So the new x will be direction 0 plus x. The new y will be direction 1 plus y. Only if the new x is valid. We should be very familiar for this part. We check whether it is valid. Greater than 0, and the new y is less than m. And what's that? It cannot be a wall. So grid new x char at new y not equal to the sharp sign. Okay, we have 3 cases, if you still remember. We first get the chart. The first case is if the chart is a capital number less than f. We want to check whether we have this key. So whether we have this key is just this part to check whether the n right shift, how many bits we should shift. It should be ch minus a, right? Like if it's a, we right shift 0. If it's capital B, we right shift 1. Okay, we right shift and we and 1. Okay, we use a parentheses. Parentheses 1. If it equal to 1, that means that we have that key. And also, we need to check we haven't visited before, so we need a visited array. So what's the size of this visited array? new int. The first one should be n, and also this is the keys. Is that keys? No, it should +1. Why? Because for this example, this key equal to 3. But if you write 3, then we cannot include the 3. The maximum is 2, so we should +1. Okay. So weighted, there will be new y, that will be key. If it equal to 0, we haven't weighted before. What should we do is weighted the new x, new y key equal to 1, and we include that, offer that new int, new x, new y, the steps +1 because we have one move. Here is the key. We did not change this key because this is a lock. Otherwise, if it's greater than a and ch less or equal than f, we first set it. So the new key will be set the corresponding bit to 1. How do you set it? It's n or the ch minus a. It should left shift. It should be one left shift. This bits. So now we get a new key. So this is just this one. We set the case bit to 1. Okay. What should we check? If we haven't weighted before, there will be new x, new y, new key equal to 0. We haven't weighted before, so we weighted and include it. There will be new key equal to 1, and there should be new key because we connect a new key. Else, the rest part is we also need to check whether we have weighted before. So if we haven't weighted, there will be key. There will be key. So there will be key. So in the end, return -1. Let's see whether it's correct. So chart. For directions. Okay. Okay. Metafy, so it's 43. So for the weighted array, count plus -1, so +1, and length. Okay, let's check what goes wrong. So this is correct, valid, not equal to sharp. Char will be that one if it's great. Yes, we want to check whether weighted before. So what's the index 5? So it's 43. New key. -a, left shift 1, and n or n. What's n? Sorry, it's not n. This is key, because this is the previous key. We want to set is this bit to 1. So this is key, not n. Sorry, that should be correct. Okay, thank you for watching. See you next time. Sorry, there's some problem. Okay, let's see. So it's at, we offer it. Is that A2F? Yes, it's A2F. So it's keys. Let's see what's wrong. that direction. Correct. Not equal to, so and if equal to haven't weighted, we have this key haven't weighted equal to 0. We set it to true, and this is key. If it's a key, we set it, and if we weighted to 1 of it, new key. Else, if we weighted the key equal to the haven't weighted, we set it to 1, and we offer new. Seems correct. So there will be 1. Cannot figure out what's going wrong for this part. Equal to 1 has. If we weighted equal to 2, if we weighted new to I think the problem is here with at y is 2, because we should go here. Why we cannot? Oh, the problem is that I can go it. Oh, I see. Rel should be -1. So, let's see. We first let this at ij to the q. Count is 1 and 1, so VT will be 2, and we pour the position here, and current key is 0, 0 not equal to 1, and direction plus I think the problem should be here. If equal to wrong, so we let this right shift. It should be correct. Right shift. This part right shift ch minus k. If it's and 1 equal to 1. That means we already kept that key. We weighted so what's wrong? Weighted. It cannot go here. Let's see what's the problem. Why it can go here? Ah, sorry. The same problem is not n is key. Because I write n here, so I always write n here. Actually, this is a number. Okay, the given number n. So here it should be key. Oh, that's a serious problem. You should always keep it the same. Okay, I think currently it should be correct. Okay, thank you for watching. See you next time.